Okay, so our second paper is presented by Evgeny Frolov, and it's called 50 Shades of Ratings, How to Benefit from a Negative Feedback in Top-End Recommendation Tasks.
Thanks. Hello, everyone. I'm a PhD student at Caltech University, and that's my first ISM RecSys conference. And I'm really excited to present our joint work with my supervisor, Oseledets. And I will start with the very simple example. Let's say we have a movie recommendation system, and we have a new user who provides his first feedback, which is a 2-star rating to the Scarface movie. And now, if you will use some standard matrix factorization or similarity-based model, you'll get a list of recommendations similar to this. And, well, user may seem to be not a fan of criminal or violent movies, so this list of recommendations seem to be irrelevant because it's insensitive to initially negative feedback from the user. And there is a sort of shift of recommendation perspective. We want to predict some relevant items, not from what user likes, but actually from what user dislikes. And it doesn't seem like a hard task for collaborative filtering models because, well, if users may share what they love, then they certainly can share what they hate. And the collaborative filtering model could use both of commonalities to predict something relevant. So why does this fail? And I will use, for illustration, a matrix factorization approach. And without the loss of generality, I will use a pure SVD, which was shown to be a strong starting algorithm by the known work of the Paolo Cremonesi, who is here today, and Yehuda Koren and Roberta Turin in 2010. So in pure SVD, the missing values are simply imputed with zeros, and then you compute a singular value decomposition. And when a new user is introduced to the system, it corresponds to the new user, a new row in the rating matrix. And of course, we don't want to recompute a full SVD, just recommend something for this new user. So we'll use a standard, well-known folding in approach, which in our case turns into this really nice expression, which basically is a projection of the user preferences, decoded by vector P, onto the latent space of items features, right? And then the top-end recommendation task is simply a ranking of this vector R, which is a vector of predicted scores. And here's the problem. If we have only single feedback, then this vector P will have only one non-zero value. And then it doesn't matter what value it is, because it does not change the ranking of the scores. It only scales them uniformly. So, OK, you may say that who cares, because we anyway don't have too much information about the user, so we probably should use a standard rating elicitation procedure. But this procedure comes with a number of drawbacks and limitations that make engagement of the user with the system less effortless and less enjoyable. And we would, of course, would like to avoid that. And it has nothing to do with the personalized experience of the user, right? Which he may or she may expect from us. So what we would want is the model that is able to produce some meaningful recommendations even from a single feedback with respect to the polarity of the feedback. And we don't want to use any heuristics or side information to keep it simple. And of course, we want that model to generalize well on common recommendation scenarios, not only cold start. So in order to do this, we have to kind of restate the problem formulation. So in a standard model, we use ratings as a measure of utility, as a cardinal values. But what we propose is to use ratings as a third categorical variable, which is learned within the model. We call this a collaborative full feedback model, or COFFEE for short. And so there are various ways how you can do this. For example, you can use factorization machines. We propose to encode those user item rating triplets as the coordinates into a multi-dimensional, three-dimensional array, which I will call a tensor. And then, similarly to a matrix case, we can use some factorization technique for example, Tucker decomposition in order to find a factors, a latent representation of users, items, and now ratings as well. And the choice of the decomposition, the Tucker decomposition, is actually beneficial here because it also allows us to use, well, kind of same idea of folding in technique, which allows us to avoid recomputation of the tensor factorization for every new user. So the only difference there is that now a new user is represented not by a vector of preferences, but as a matrix of preferences, right? Which has items along one dimension and ratings along another dimension. And following the same reasoning, we could get a very nice and very similar expression for the predicted scores. And again, it's not a vector anymore. It's now a matrix. And the W here, actually, it's an embedding of those ratings onto the latent feature space. Okay, so we call this a shades of ratings, and the explanation comes from the next slide. So this is an example of the predicted scores for a test user, a single user, and the more dense colors represent higher relevance scores. So you can see that now our model gives more rich information about the user. It's kind of a granular view on all kinds of preferences of the user with respect to all kinds of feedbacks. Right, and this model is equally sensitive to any kind of feedback, no matter how positive or negative it is, right? And it doesn't make any assumptions on the nature of the feedback, and the feedback, how users rate the items is learned within the model for every individual user and an item. So now for the top-end recommendation task, we simply rank the scores along the column that corresponds to the maximum rating value, which is 5 in that case. And we also can solve the rating prediction task, which is simply a ranking not along the column, but along the rows of this matrix. So let's go back to this first example. When we use that model, the coffee model, we get this recommendation list, which now starts to make sense, right? Those movies kind of have different even opposite features. And we played with the model and to see that it produces consistent results for different examples. However, when we started to do some more general evaluation, we realized that this improvement of the model is not reflected by any standard metric. And it's easy to see why. For example, for the case of precision, in its general definition, there is an implicit assumption that all the items that are recommended to the user are considered to be interesting. But it may not be the case because, well, the items from the holdout set that we evaluate our recommendations against, they can contain, they can have not only positive feedbacks, right? They can have also negative feedbacks. And also for the ranking, for example, for an DCG score, again, the contribution of all the recommended items simply increases the gain. Well, for the negative feedback, the gain will be lower, of course, but again, it increases the gain, which doesn't make sense because, well, low ratings do not express my enjoyment with the movie, right? So we need to somehow to split this concept of relevant and irrelevant recommendations, and it's easy to do. So when we recommend something and it has the true rating assigned by user is positive, then, well, it's a true positive prediction. If we recommend something and it has negative rating, that is false positive. Similarly, if we do not recommend something and it has a positive rating, then it's false negative, and if the negative feedback, then it's true negative, right? So the last case is when we recommend something and it doesn't have any feedback from the user. And I will use some kind of presumption of innocence here because we don't know the rating. right? So it might be positive, might be negative, we don't know. And in standard models, these assume to be false positive. But I will simply ignore it and will leave it unclassified. So now the relevance-based metrics take a canonical form, which is very nice. In DCG metric, we use only positively rated items to evaluate the gain. And we also introduce a new metric, which we call discounted cumulative loss, which is kind of opposite to the DCG, and it kind of measures the overall disappointment that user will get with our recommendations. And now, so here's the result. The first is a precision against the recall. And that's the cold start scenario with single negative feedback. So from here, you can conclude that probably the popularity-based model, which is a yellow line, is the top performer, and it's the best option for us to use in that limited information case. And this conclusion kind of supported by the NDCG, where we still see that popularity-based model is the best model, but we also see that coffee model, which is a green line, surprisingly goes really low. However, if we'll look at the NDCL metric, that's cumulative loss, we see that our coffee model actually performs very good. So it avoids recommending irrelevant items. And now recall this presumption of innocence concept. It means actually that our model kind of pushes the items that the user have not rated yet. That's why this NDCG rating is so low, because there is no reason to assume that our coffee model performs worse because it still has really high precision recall curve, right? And for the more general scenario, when we have a lot of information about the user, our model performs at the same or even higher level as the other models. And again, we see the same picture, that it has a little bit lower in DCG and much lower in DCL. And in that case, a popularity-based model has lower in DCL, but it doesn't matter because it's not a top performer anymore. So key takeaways from here is that, well, standard evaluation metrics kind of obscure a part of the evaluation of the performance of the models. And it's really important to take the negative feedback into account, both in the models and in evaluation. And it's also natural to represent user feedback not as a cardinal values, but as a ordinal concept. Right? And it can be efficiently done with tensor approach, which gives you an opportunity to produce instant recommendations like with the SVD case, so it can be used online. And finally, the coffee model can alleviate the rating elicitation problem, because the model now, it kind of, when it has not enough information, it makes a safe guess. So it can learn user preferences gradually from the very beginning, from the very first feedback, avoiding irrelevant items, which means avoiding disappointment of the user, much better than any other model. And during the preparation of this work, we have developed a Polara framework, which takes into account all those polarity feedback stuff. And it's also easy to use. We've put special effort to make it like RecSys for humans. And if you want to reproduce the results of this work, you can do this by going to that link. And even more, you don't have to install anything. Thanks to Binder, you can do it right in your browser. And this is it. And thank you for your attention.
So thank you very much. We've lots of time for questions. So have we got a... Yes, thank you.
Thank you for the great talk. I totally agree that it's scalable and it's usable in online kind of use cases. Could you share some light about the complexity of trained side? For example, for SVD, we have approaches like ALS that can be scalable to compute it on several machines. Mm-hmm. Is Tucker decompositions possible to scale?
So again, so there are like two circuits, right? First, we train the model and we get those factors like V and W, right? So as long as you have them, you can recompute the model offline, like in any way you like. You have the factors, and you can produce recommendations with those factors independently, right? So it doesn't matter actually how complex your data is, as long as you have those factors. When your model recomputed, you just update the factors, and then you're ready to produce new recommendations. And even more, so this folding-in technique, you can actually update instantly. Not only well, you can update the model itself instantly, right? So it's very similar to an SVD. So
yeah, I totally agree with fold-in approach. My question is about train phase. Is it scalable?
Yeah. So Tucker decomposition is basically a sequence of SVDs on the it's unfolded tensor, let's call it. So I don't have this on the slide, but it's in the paper. If you will compare the training time for the coffee model, it's even lower for the matrix factorization cases, not SVD, but for the BPR and for weighted matrix factorization.
Okay, thank you.
Thank you very much.
Hey, hello. My question is there any reason for you to employ the Tucker rather than the CP in your tensor model?
Yeah, exactly. So that's the first thing is that Tucker gives you orthogonal factors which are important to make this folding-in approach working, right? In case of SVD, in case of standard matrix factorization, it's not really well, you can always orthogonalize the factors, right? But it's an extra step. So Tucker gives you this orthogonality of factors just out of the box, right? That's the first thing. And the second thing is that canonical decomposition is unstable generally, right? And Tucker is stable. So that a canonical decomposition works well when you have more structured data. For example, you have a number of sources on signal, right? And you know the number of those sources. Then canonical decomposition will be most likely stable and will recover all the information needed. But in our case, we cannot make any assumptions on the nature of the data, right? It's just users and items, and it's more like not random, but it has really complicated structure, and there is, it's really hard to uncover it with the CP decomposition.
Okay, thank you. Another question? Yes, thank you.
Hi, thanks for the great talk. I had a question. When you said that the model, when you evaluated it, you picked the item with the highest likelihood of having a maximum 5-star rating from the user. This likelihood can still be pretty low, right? Did you consider also looking at different kinds of positive ratings that might have higher likelihood, like 90% chance that this user will give a 4-star rating might probably be better than 10% chance of getting a 5-star rating, something like this?
I didn't quite get, so what do you mean by the likelihood? Because I didn't say that it's likely. Can you repeat what's the likelihood?
You said that the model's prediction, we were going to look at the column with the maximum rating and rank all of the items based on the likelihood of this user ranking this item with 5-star, right? So as far as I understand, you completely excluded the values for the 4-star rating, which is also a positive in our scenario. Right, so instead of, did we also run?
Yeah, I get it. So, that's a simplification. Actually, in our work, I use the combination of rating 4 and the rating 5. And you can use any kind of weighting for those scores. So you can in the simplest case, you can just sum them up and then do the ranking. So that's a lot of, degrees of freedom for experimenting and finding the best combination for getting the best scores.
Thanks.
Okay, thank you. We had one last question. Just, it's curious to me why your ratings and your relevance is not monotonic here, that the relevance isn't getting higher with ratings. So you have a big white column here on this slide at rating 4.
Which one?
The one that you just had there.
Okay.
So just the one that was just there just a second ago?
This one?
No.
The slide with the shades?
The slide you were showing us there, where you have your ratings and your relevance is
you mean that's the kind of sparsity pattern in this rating shades?
Yeah.
Oh, that's very easy actually. So I did not use any complicated models for dealing with the long tail. So I mostly I try to compare with the more like popularity tuned models, right? So I used low ranks, and with low ranks you kind of lose lots of information, and then you start seeing this, like it kind of smoothes everything. So that could be a possible reason for why you see here. And I use that picture just for for example, for illustration. You can have really complicated structure of these metrics. Yeah.
Okay. Thank you very much.
Thanks.